In this section, we'll take a look at the parts of the airplane that provide the thrust necessary to sustain flight. In addition, while gaining a basic understanding of how the power plant operates, you'll learn how you, as a pilot, can monitor and control the engine and propeller. In many ways, the engine in an airplane is similar to the engine in your car. Both produce mechanical energy through a cycle which occurs within the cylinders. There are 4 strokes to every cycle: intake, compression, power, and exhaust. The first part of the 4-stroke cycle is the intake stroke. As the piston moves away from the cylinder head, the intake valve opens and a combustible fuel and air mixture is drawn into the cylinder. Next, the mixture is compressed as the intake valve closes and the piston moves back toward the cylinder head. When the compression stroke is almost complete, both spark plugs ignite the mixture. The combustion drives the piston away. This creates the power necessary to turn the crankshaft. Finally, the exhaust valve opens and the burned gases are forced out of the cylinder. In light training aircraft, this cycle repeats itself approximately 1,300 times a minute during cruise flight. The same cycle is taking place in each of the other cylinders. However, the sequence is staggered, so a power stroke is always being applied to the crankshaft. This provides you with a smooth-running engine. Since the crankshaft is connected to the propeller, its rotation causes the propeller to spin and produce thrust. The cylinders on an air-cooled engine are cast with thin fins, which increase the surface area. Heat from the cylinders passes into these fins and is carried away by the airflow around the engine. Now that you have a basic understanding of the engine, let's take a look at the various systems that help you monitor and control it. Let's begin by taking a look at how the engine receives the spark necessary to ignite the fuel and air mixture in the cylinders. The basic source of current is a magneto, which produces a hotter spark at higher engine speeds than does the battery system used in your car. The magneto fires as soon as you engage the starter and will continue to fire as long as the crankshaft is turning. There are actually 2 magnetos for each engine, which means the airplane has a dual ignition system. Since the 2 magnetos are independent of one another, each one fires a different spark plug in each cylinder. This makes it possible for the engine to run on either set, so that your engine will continue to run safely if one magneto or spark plug fails. Besides being a safety factor, having 2 spark plugs in each cylinder improves the combustion of the fuel and air mixture, resulting in more engine power. The airplane's ignition switch controls which magneto you're using. For example, after the engine starts, normal flight conditions require the use of both magnetos. Before you take off, however, you can test the independent performance of each side. Just how you perform this check will be discussed in the pre-takeoff checklist section of takeoffs and landings. When shutting down the engine, it's very important that you remember to turn the ignition switch off. If it is left in the right, left, or both position, the engine could still start if someone moves the propeller from outside the airplane. Turning off the master electrical switch without turning the magnetos off will not prevent the engine from starting, because the magnetos are separate from the rest of the aircraft's electrical system. To achieve the best performance from your engine, each cylinder must receive the proper fuel-air mixture. The engine induction system lets you regulate the proper mixture required during different flight conditions. Before the mixture enters the cylinder, a carburetor meters the correct amount of fuel and then combines it with filtered air. The carburetor, however, is calibrated to provide the proper fuel-to-air combination at sea level when the mixture control lever is set in the full rich position. But as you have learned, the density of the air decreases as you climb to higher altitudes. Subsequently, the density of the air entering the carburetor will decrease, while that of the fuel remains the same. This means that the mixture becomes too rich, or there is too much fuel for the density of the air entering the carburetor. A mixture control lever or knob is located in the cockpit. It enables you to adjust the amount of fuel to maintain the correct fuel and air blend at varying altitudes. If you fail to adequately lean the mixture as recommended in the pilot's operating handbook, the engine will run rough. An overly rich mixture causes a cooling effect in the cylinders. This can foul spark plugs and valves, resulting in a loss of power. On the other hand, if you lean the mixture too much, the engine temperature will become very hot. A mixture that's too lean can cause detonation and/or pre-ignition, which can damage or even destroy major components of the engine. Detonation is the explosive combustion of fuel in the combustion chamber, rather than the smooth burning that normally occurs. It can develop whenever you allow the engine to overheat. Besides occurring with an excessively lean mixture, it can also result from using an improper fuel grade. Other causes include taking off when the engine is near maximum allowable operating temperature, and flying with a high power setting and low airspeed configuration, which may not provide adequate engine cooling. A different form of abnormal combustion, pre-ignition, is caused by a hot spot in the cylinder and occurs when the fuel and air mixture ignites prematurely. This hot spot may be a carbon deposit on a spark plug or any damage found around the combustion chamber. Another potential source of engine roughness and possible fuel starvation is carburetor icing. Because of the rapid cooling that takes place inside the carburetor when fuel vaporizes and the air expands, moisture can condense, freeze, and begin adhering to the internal surfaces. This accumulation of ice can substantially restrict or even cut off the fuel-air mixture to the engine. Although carburetor icing can occur over a wide range of conditions, it is most likely to form when the relative humidity is above 80% and the temperature is below 21 degrees Celsius or 70 degrees Fahrenheit. In most training airplanes with a fixed-pitch propeller, the first indication of carburetor ice and the subsequent power loss is a gradual decrease in engine RPM, which may not be readily noticeable. If this situation occurs, you should apply carburetor heat. This routes heated air into the carburetor to melt the ice. On some of the airplanes that you'll fly, a fuel injection system is used instead of a carburetor as a more precise way to meter the fuel and distribute the fuel-air mixture to the cylinders. Although fuel injection is typically a more expensive type of induction system, it has several advantages over a carburetor. These include a more even fuel distribution to the cylinders, which reduces operating temperatures, improved acceleration, and lower fuel consumption. The system is also less susceptible to induction icing. Although fuel injection has many benefits, you may experience some problems with the system, particularly when attempting to start a hot engine. The problems occur after shutting down the engine as the air temperature inside the tightly enclosed cowling increases. The temperature inside the induction system can reach a point where the fuel vaporizes, creating a vapor lock, which effectively blocks the fuel flow. Although the specific starting procedure varies, an auxiliary fuel pump is normally used to clear the fuel vapor and reestablish the fuel flow. Fuel vaporization can also occur during ground operations due to inadequate engine cooling, and you might have to use the fuel pump intermittently to purge the vapor lock and prevent fuel starvation. Whether you fly airplanes with a carburetor or fuel injection, engine efficiency decreases as you gain altitude, and thus the density of the air entering the engine is reduced. To overcome this drawback, some engines incorporate a turbocharger that compresses the air that enters the combustion chamber. This increases the density of the air. Ultimately, The airplane is capable of operating at higher altitudes, since the engine can continue producing sea-level power as you climb. During your pre-flight check, you should make sure the oil level is correct, because after the engine is running, the moving parts are lubricated by engine oil. This oil also helps to keep the internal temperature of the engine within acceptable limits. The heart of the oil system is the pump, which draws oil from the sump, pumps it through an oil filter and cooler, and then routes it to the engine. Gauges on the instrument panel display the oil pressure and temperature. A green region normally shows the correct oil pressure. If you observe an abnormal indication, you should assume that the engine parts are not receiving adequate lubrication. An oil temperature gauge lets you keep an eye on the system by displaying whether or not the temperature is in the permissible range. On many light airplanes, this gauge is the only indication of engine temperature. If the engine is running a little hot, you can assist in the cooling process by using a richer mixture setting, reducing your rate of climb, increasing airspeed, and reducing the power setting. The second part of the power plant is the propeller, which produces the thrust necessary to move the airplane through the air. The propeller consists of a hub and 2 or more blades. Since each blade is an airfoil, it is subject to the same aerodynamic factors that apply to any airfoil. The camber of a rotating propeller creates a lower pressure area in front of the blades, just like a wing creates a lower pressure area above the airfoil. This produces the horizontal lift or thrust necessary to propel the airplane through the air. However, unlike the wing, which is traveling at a uniform rate in straight and level flight, the tips of a propeller are traveling through the air faster than the area near the hub. Therefore, a propeller blade is twisted with less angle near the tips. This creates uniform thrust along most of its length. The overall angle of the blade determines its operating efficiency in various phases of flight. A propeller with a low blade angle is capable of producing more RPMs and is best suited for takeoffs and climbs. A blade with a high angle, however, is more efficient for cruise flight. Most light training airplanes use a fixed pitch propeller with an overall blade angle somewhere between a true climb propeller and one designed just for cruise. This provides relatively efficient thrust throughout the airplane's operating range. With a fixed pitch propeller, the blade's angle cannot be changed. On airplanes with a fixed pitch prop, you control engine power and propeller RPM solely through the use of a throttle. As you add power, the increase in engine and propeller RPM is indicated on the tachometer. Some airplanes use a more expensive constant speed propeller. With this type of prop, you can vary the pitch to obtain the most efficient blade angle during the different phases of flight. Airplanes with constant speed propellers have 2 power controls, the throttle and propeller control. As you adjust the throttle, the changing power output is indicated on a manifold pressure gauge. Manifold pressure is measured in inches of mercury and represents the pressure of the fuel and air mixture inside the engine's intake manifold. The higher the pressure, the greater the engine power being produced. By advancing the throttle, you increase the fuel and airflow to the combustion chamber and thus increase the manifold pressure. Since manifold pressure is measured in inches of mercury, the gauge is essentially an aneroid barometer. This means that when the engine is not running, the atmospheric pressure is displayed. The propeller control lets you change the pitch of the propeller blades, which regulates the RPMs shown on the tachometer. Your ability to select and maintain various blade angles and RPM settings for different phases of flight is where the efficiency of a constant speed propeller is measured. Changing propeller RPMs is much like changing the gears on an automobile or bicycle, where a low gear is best during acceleration and a high gear for cruise. For instance, before takeoff, you adjust the knob to set the propeller to a low blade angle. This provides high RPMs for maximum takeoff thrust. Upon reaching cruising altitude, you adjust the blades to a higher pitch. This produces a lower RPM and provides adequate thrust for cruising airspeed. Once you've selected the appropriate RPM, the propeller's pitch will adjust slightly during varying flight conditions so that the propeller load matches engine torque and the tachometer setting remains constant. Also, as you alter the manifold pressure with the throttle, the propeller will automatically adjust its pitch to maintain the selected RPM setting. Because the propeller can be very dangerous, exercise extreme caution when you're near an airplane. Even if the propeller isn't turning, the pilot in the airplane might be getting ready to start the engine. In addition, if you are flying with passengers, you should routinely brief them about the proper procedures to follow when around an airplane. The power plant installed in today's airplane is very reliable, but to get maximum use and consistent performance, you need to operate it in accordance with the procedures and specifications prescribed in the Pilot's Operating Handbook. Now that you have an understanding of how the power plant performs, let's take a look at how the engine is provided with fuel and examine the electrical system found on most training airplanes. Let's start with the fuel system. Generally, there are two types of fuel systems which you might encounter during your training. The first is the gravity feed type commonly found in high-wing airplanes. With this type of system, the fuel tanks are usually mounted inside the wings. Because of the difference in height between the tanks and the engine, gravity forces the fuel to the carburetor. A second type of system must be incorporated on low-wing airplanes, where the fuel tanks are positioned below the engine. Here, an engine-driven fuel pump supplies fuel from the tanks to the carburetor. However, this pump only supplies fuel once the engine is running. For starting, an electric boost pump is used to supply fuel. It can also be used as a backup should the engine-driven pump malfunction. No matter which type of fuel system your airplane uses, you must determine before each flight that your airplane has been filled with the proper amount of fuel. Always verify that the tanks contain the corresponding amount of fuel that was shown on the gauges. Never rely on the fuel gauges as your sole source of determining fuel quantity. You should also ensure that the tanks contain the correct type of fuel. Airplane engines are not all alike, and each one is designed to use a particular grade of fuel. To help with identification, colored dyes are added to each type. For example, 80 grade fuel is colored red, 100 low lead is blue, 100 is dyed green, and turbine fuel is colorless. The POH lists the acceptable fuel for the aircraft you're flying. If the proper fuel is not available, using the next higher grade of fuel for a short period of time is not considered harmful, as long as the manufacturer has authorized it. However, you should never use a lower grade because it can produce excessively high engine temperatures and cause serious engine damage. In addition, you should never use turbine or jet fuel in a reciprocating engine. Another consideration during pre-flight is to check for fuel contamination. You can do this by checking the wing tank drains and the fuel strainer. If you discover water or sediment, you should continue to drain the system to eliminate all traces of the contamination. One way to minimize water in the tanks is to make sure they are filled after the last flight. This helps prevent water vapor from condensing in a partially filled tank due to temperature changes during the night. Managing fuel consumption during your flight is equally as important as checking it before you take off. The fuel quantity gauges display the volume remaining in each tank. Besides showing the number of gallons, many also indicate the fuel's weight. To help you manage the fuel use efficiently, a selector valve is placed in the cabin, allowing you to select fuel from various tanks. While many airplanes have a selector valve that allows you to draw fuel from both tanks during normal operations, others necessitate switching back and forth from one tank to another. With this type of system, you need to avoid running on only one tank for an extended period of time, since the unbalanced fuel load will affect the airplane's stability. It's also essential that you follow the procedures outlined in the airplane's POH for changing tanks to ensure an efficient and uninterrupted fuel flow to the engine. Now let's turn our attention to how the airplane's electrical system provides the power to run the avionics and electrical equipment. Most modern airplanes derive electrical energy from an engine-driven alternator, which produces alternating current and converts it to direct current. The direct current is then delivered to a bus bar, which distributes the power to the various electrical equipment. This typically includes, among other things, various lights, the radios, the turn coordinator, and gauges. Another critical component in the electrical system is the battery. Although its primary purpose is providing a means of starting the engine, it also can be used in an emergency to provide limited power to the electrical components. An ammeter mounted on the instrument panel measures the amount of current flowing to or from the battery. It provides you with the means of monitoring the electrical system. After the engine starts, the needle will deflect to the plus side to show that the battery power lost during the start is being replaced. Once the battery is charged, the needle will stabilize near zero to show you that the alternator is now supplying the current to the electrical system. If the needle begins pointing to the minus side, it means that the electrical load is exceeding the alternator's output capability and that the battery is helping to supply electrical power. A negative indication could also mean a malfunctioning alternator. If this occurs, you should reduce the electrical load by turning off non-essential equipment and land as soon as practical. The entire electrical system is controlled with a master switch. This switch is designed in such a way that the battery function can be activated without the alternator. But the alternator half cannot be activated independently. If you experience an alternator problem during flight, you can remove it from the electrical system by turning the alternator side of the switch off. Just remember that when doing so, you place the entire electrical load on the battery. In order to protect the various components from the possibility of an electrical overload, your airplane is equipped with fuses or circuit breakers. Normally, each component's name is printed on the circuit breaker panel. If an overload occurs, the circuit breaker will pop, protecting the various components within that circuit. After a short cooling period, you can reset the breaker by pushing it back in. However, if it pops again, an electrical problem probably exists, and the device should not be used until it is repaired. As with all of the airplane systems, a sound knowledge of how the fuel and electrical systems operate will help you to become a safer and more professional pilot. The aircraft POH will not only provide you with an abundance of information for normal operations, but will also detail the appropriate actions to take in the event of a system malfunction.